of knowledge or rationality, their ordinary heterogeneous ways of exercising agency. And I argue recognizing these differences helps explain why similar people facing the same information and the same recommendations can arrive at different vaccination choices. This brings us to the key question. Why are these differences in how people approach health decisions so consistent? They're not random. They're not well explained by intelligence, information, or rationality. And psychology offers a range of ideas here, including differences in tolerance for uncertainty, reliance on expert cues, and preferred strategies for acting under risk. I draw these strands together using a framework that we call the medical mind, which organizes health decision-making preferences along three simple continua. These are not ideologies or personality types, but stable ways people tend to engage with medical choices. In the next section, I'll show how we measure these preferences and how strongly they relate to vaccination attitudes and behavior. So now we turn to the core empirical part of this talk. Up to this point, I've been describing a familiar experience, people facing the same medical recommendation and responding in predictably different ways. The question is how we can capture those differences systematically rather than treating them as anecdote or noise. So in the next few slides, I'll introduce my framework for health decision-making preferences, show how we measure it in nationally representative survey data in the United States, and then show how strongly it relates to vaccination attitudes like confidence and hesitancy, and to outcomes closer to behavior, like intent to vaccinate and vaccine uptake. My goal is to move from the lived phenomenology of medical choice to an empirical map of how agency is distributed in the population. So to describe pattern differences in how people approach medical choices, together with my colleagues, I draw on a framework introduced by Jerome Groopman and Pamela Hartzman in their book, Your Medical Mind. This framework did not emerge from a formal decision theory, but from clinical experience. Groopman and Hartzman were trying to make sense of a recurring observation. Patients with similar diagnoses and recommendations engage with those recommendations in systematically different ways. What makes the framework useful for our purposes is not that it claims to be a comprehensive theory, but that it offers a clear structure for organizing these observations. The core of the theory is to identify three continua along which people tend to differ. The first is being a minimalist versus a maximalist. Some people prefer to intervene only when absolutely necessary, while others favor early or decisive action to prevent future risk. The second is being a naturalist versus a technologist. Some people are more comfortable with natural processes and low-tech remedies, while others place greater trust in biomedical or technological solutions. And the third is a doubter versus a believer. Some people routinely question and cross-check medical advice, while others are comfortable relying on professional authority. These continua are not personality traits, and nor are they ideological commitments. People do not fall neatly into categories. Instead, they describe stable tendencies in how individuals navigate uncertainty, weigh expert advice, and experience their own agency in medical settings. Clinical phenomenology is often where formal theories begin, and our goal has been to take this intuitively rich framework and examine whether it can be observed, measured, and tested empirically in the context of vaccination. To operationalize this idea, to move from clinical intuition to empirical analysis, we designed survey items that capture how people typically approach medical decisions. Each of the three continua is represented by multiple questions reflecting its core logic, whether one tends to avoid or favor medical intervention, one is more comfortable with natural remedies or biomedical technologies, and whether one typically trusts medical advice or prefers to double-check it. It's important to be clear about what this does and does not mean. We are not diagnosing individuals, we're not measuring fixed psychological traits, but estimating tendencies at the population level. These are probabilistic patterns. These items were then fielded in a large nationally representative survey conducted between 2016 and 2014 in coordination with the National Opinion Research Center at the University of Chicago. Within each dimension, responses correlate in the expected ways, indicating that they're capturing coherent underlying tendencies, not isolated opinions. That consistency suggests we're not simply measuring reactions to specific events or controversies, but relatively stable features of how people approach decision-making. When we example these preferences in large samples, the first thing we see is that they're not categorical. They are genuine continua. Most people fall somewhere near the middle of each dimension, but there is meaningful representation across the entire range. No orientation is rare, extreme, or pathological. This matters empirically because it tells us we are not studying fringe positions, as vaccine hesitancy and confidence are often cast. Rather, these are ordinary differences in how people engage medical advice. It matters normatively because it cautions against framing vaccination behavior in moral binaries, responsible versus irresponsible, rational versus irrational. The variation we observe reflects diversity in decision-making style, not deviance. When we repeat the surveys in independent samples, the distributions look almost identical. The stability suggests that these dispositions are part of the background landscape of health decision-making, not transient responses to news cycles, pandemics, or political moments. Up to this point, we've focused on individual-level psychology, how people engage with medical advice, how preferences shape intent, and how intent sometimes, but not always, becomes action. The challenge is then to translate these individual processes into population-level consequences. Psychology studies individuals, but epidemics are a collective phenomenon. The bridge between them is aggregation. Decisions about whether to vaccinate, when to vaccinate, and whether to delay do not just affect individuals. When repeated across populations, they shape overall coverage, and that's what determines seasonal influenza dynamics in the US. This is where the analysis turns from understanding behavior to understanding consequences. This slide shows the relationship between vaccine confidence and vaccine hesitancy. As expected, they are strongly related. People who are more confident tend to be less hesitant. But they are not the same thing. There is a wide middle ground of people who recognize the benefits of vaccines, yet still delay, deliberate, or feel unsure. One way to think about this distinction is that confidence is largely epistemic, answering the question, do I believe this works and is safe? Whereas hesitancy is often procedural, answering the question, what do I do now? People can be confident in the evidence and still hesitate because they want to time the decision carefully, consult others, or wait until the recommendation feels personally relevant. This distinction matters because many interventions implicitly assume that increasing confidence will automatically eliminate hesitancy. Our data suggests this is not the case. Hesitancy frequently reflects how people prefer to act under uncertainty, not whether they accept the underlying science. On this slide, each panel shows the relationship between one decision-making preference and vaccine hesitancy. As you move along the horizontal axis, you're moving from one end of a continuum to the other. For example, from more minimalist to more maximalist, from more doubting to more trusting. The vertical axis shows average levels of hesitancy. What's striking is how consistent the pattern is across all three dimensions. In each case, as people lean toward more maximalist, technologist, and believer orientations, vaccine hesitancy declines. As they lean toward minimalist, naturalist, and doubter orientations, hesitancy increases. These relationships are smooth, not abrupt, which reinforces the idea that we're looking at continua, not categories. It's also important to emphasize what these relationships do and do not mean. These preferences are measured independently of vaccine attitudes, and they're not simply proxies for political identity, trust, or knowledge. They still explain a meaningful share of variation in hesitancy, even after those variables are accounted for. That tells us that hesitancy is not only about what people believe or how much information they have, it's also about how they characteristically prefer to engage with medical decisions when uncertainty is involved. This slide shows the same decision-making preferences distributed across age groups. Each box summarizes the distribution for a cohort, showing both the central tendency and the spread. What you should notice first is that every age group contains the full range of preferences. There are minimalist and maximalist young adults and minimalist and maximalist older adults. What changes with age is not the range, but the center of gravity. On average, older adults tend to lean more maximalist, more technologist, and more trusting of medical advice. Younger adults, on average, lean in the opposite direction. This matters because age differences in vaccination behavior are often explained purely in terms of clinical risk, access, or transmission rate. What this slide shows is that age often captures systemic differences in how people, on average, engage with medical recommendations. Those psychological differences sit alongside biological vulnerability and contact patterns, and they become especially important when we later consider epidemic dynamics. Here we move one step closer to behavior by looking at vaccination intent. Each panel corresponds to one decision-making continuum, and each point represents an individual respondent. As before, the horizontal axis shows where someone falls along a preference continuum, and the vertical axis shows their reported likelihood of vaccinating. The fitted lines show the average relationship between decision-making orientation and intent. The pattern closely mirrors what we saw for hesitancy. People who lean toward maximalist, technologist, and believer orientations consistently report higher intent to vaccinate. Those who lean toward minimalist, naturalist, and doubter orientations report lower intent. These relationships are smooth and graded, reinforcing that we're looking at preferences, not categories. It's important to keep the size of these effects in perspective. At the level of any single individual, the effects are modest, which is exactly what we would expect. Vaccination intent reflects many influences, including past experiences, access, social norms, timing, and perceived relevance. But taken together, these three decision-making orientations explain on the order of 20% of the population-level variation in vaccination intent. In large, diverse survey samples, that is a substantial amount of explanatory power for broad psychological predictors. This is why these preferences matter beyond individual psychology. Even modest shifts in average intent, when aggregated across millions of people, translate into meaningful differences in vaccination uptake. And those differences, in turn, shape population-level vulnerability and epidemic dynamics. This slide shows the well-known gap between intent and behavior. On one axis, you see what people reported about their likelihood of vaccinating. On the other, what they actually did in the following season. As expected, intent matters. People who report higher intent are more likely to be vaccinated, but the relationship is far from perfect. What's important to notice is the spread. Even among respondents who said they were very likely to vaccinate, a substantial fraction did not follow through. And conversely, some people who expressed low or uncertain intent never ended up being vaccinated, or did end up being vaccinated. This gap tells us something important about how vaccination decisions unfold over time. Intent captures a person's orientation at a particular moment, how they feel about a recommendation when asked. But between intent and action lie many practical and psychological steps, including scheduling, competing priorities, changing perceptions of relevance, social context, and evolving interpretations of risk. The key point is that intent is only one stage in the decision process. To understand vaccination behavior, we need to understand not only what shapes intent, but how people translate intent into action, or they fail to do so. That transition is where decision-making preferences, timing, and situational constraints begin to matter in a deeper way, and where individual agency connects most directly to population-level outcomes. Putting this together, we see that there's a sequence. Decision-making preferences shape how people engage with medical advice. That shapes intent. Intent sometimes shapes action and sometimes does not. When these small, partly predictable differences are aggregated across a population, they determine overall coverage. Even modest shifts in coverage can change epidemics' timing, size, and severity. This is the bridge from individual psychology to population-level disease dynamics. So how do we identify what these population-level disease dynamics are? Psychology studies individuals, epidemics are a collective phenomenon. The bridge between them is aggregation. Modest differences in timing, follow-through, or uptake alter population-level coverage. To study these collective effects, we used a mathematical model. The purpose of this model is not particularly prediction. It's not designed to forecast a specific influenza season, but it's explanatory, low-dimensional. It allows us to examine in a controlled way how differences in vaccination behavior translate into differences in epidemic outcomes. At the individual level, a 5 or a 10-point difference in vaccination probability may seem modest. At the population level, those differences might substantially alter the timing of epidemic peaks, total number of cases, and number of severe outcomes. Modeling provides a way to make those nonlinear consequences visible and intelligible. Our model is age-structured. Age serves as a pragmatic proxy for several things that matter simultaneously: contact patterns, clinical risk, and systematic differences in vaccination behavior. Age groups differ in how often they interact, how vulnerable they are to severe disease, and how likely they are to vaccinate. Importantly, age is also correlated with differences in medical decision-making tendencies. Older and younger adults differ on average in how they engage with medical advice. The model does not represent psychology explicitly, but incorporates its effects indirectly through age-specific vaccination behavior. This is a simplification, it's true, but it's a transparent one. And you may be thinking, well, age isn't psychology, and of course you're correct. However, if anything, this simplification likely underestimates the effect of behavioral heterogeneity. In our model, the population is divided into age groups with different contact rates and different propensities to vaccinate. We use a standard age-structured epidemic framework similar to a multi-group SIR model combined with our empirically estimated age-specific vaccination rates from our survey. The epidemiology itself is conventional. What is new is feeding a realistic behavioral landscape into the model. When vaccination behavior varies systematically across age groups, those differences interact with contact patterns to reshape epidemic dynamics in ways that would be invisible in a homogeneous population. So before showing results, let's explore the structure of the model in a little bit more detail. As mentioned, the model is written as a system of differential equations, which simply track how quantities change over time. This is the standard way in epidemic modeling of describing how people move between health states as infections spread and resolve. This is, of course, a compartmental model. The population is divided into mutually exclusive categories: susceptible, infected, recovered, and vaccinated, and individuals move between these compartments over time. Births add individuals to the youngest susceptible group, and deaths remove individuals from the system. For today's focus, I evaluate the model for a single influenza season rather than investigating long-term dynamics. Transmission is age-structured. People mix more with their own age group than across groups, with realistic cross-age contacts between children and parents or grandparents from the Polymod study, a diary study that measured real-world social contacts. Influenza transmission is also seasonally forced, and we do that as well, with transmission peaking in the winter. Vaccination enters the model as a continuous time rate at which unvaccinated individuals move into the vaccinated compartment. These rates are estimated from survey data. Specifically, we use a regression model that predicts vaccination probability from age and average health decision-making preferences, then convert those probabilities into age-specific vaccination rates. Psychological preferences do not appear as explicit compartments, but instead influence epidemic dynamics indirectly through their effect on observed vaccination behavior. Vaccination provides two forms of protection. It reduces the probability of infection, and conditional on infection, it reduces the risk of severe disease and death. Both effects are included using published estimates from the U.S. Centers for Disease Control. With this structure in place, we can examine how differences in vaccination behavior shape outcomes. This slide shows a reference epidemic generated under current vaccination behavior. It represents the status quo, observed age-specific vaccination rates, realistic contact patterns, and no additional intervention. This is not a forecast, but a baseline for comparison. The resulting epidemic resembles a typical influenza season in the US in both timing and magnitude, which gives us confidence that the model captures the essential structure of the system. From this baseline, we can ask how changing vaccination behavior alters epidemic outcomes. To compare vaccination strategies fairly, we impose a constant effort constraint. Each strategy uses the same total vaccination effort. Effort reflects not just the number of additional vaccinations, but also how difficult they are to achieve, recognizing that some groups are easier to vaccinate than others. Under this constraint, we consider three strategies. A broad strategy spreads effort evenly across all ages. A priority strategy concentrates effort on age groups with the lowest baseline coverage. And a behavioral strategy targets age groups whose decision-making profile indicates a stronger disposition toward vaccination, and therefore a greater likelihood that effort will translate into uptake. This setup deliberately forces trade-offs. Equal effort does not produce equal outcomes, and different allocations reflect different implicit priorities. When we compare epidemic outcomes under these three strategies, holding total effort constant, we see a divergence in what each strategy optimizes. Priority targeting produces the largest reduction in total cases because it focuses on groups that contribute most to transmission. Behavioral targeting produces the largest reduction in deaths because it concentrates protection in groups that are both more vulnerable and more likely to vaccinate. This highlights an important tension in vaccination policy. Reducing transmission and reducing mortality are not always aligned goals. How vaccination effort is allocated can shift the balance between these outcomes, even when total resources are fixed. Understanding behavioral disposition helps clarify those trade-offs rather than obscuring them. To conclude, I want to step back from these data and the models to the idea that motivated the work in the first place. Throughout the talk, I've shown that people differ not just in what they believe about vaccines, but in how they engage with medical advice, and how they balance autonomy and authority, caution and intervention. These differences are not noise, but they are patterned, measurable, and consequential. When aggregated, they shape vaccination behavior and epidemic outcomes. This brings us to a view of agency that is plural rather than uniform, something enacted in different ways under different constraints by different people. Public health often speaks as if there were a single kind of decision maker, someone who processes information uniformly and acts predictably once persuaded. Our findings suggest that this assumption is incomplete. People enact autonomy differently. They rely on different cues, tolerate uncertainty differently, and move from advice to action along different paths. Ignoring this plurality can lead to brittle policies and frustrated communication efforts. Recognizing it opens the possibility of designing interventions that respect diversity and agency while still advancing collective goals. The medical mind framework provides one way of making this plurality visible. The three continua capture stable orientations toward medical advice and action, helping explain why vaccination behavior cannot be reduced to misinformation or risk perception alone. The core contribution of our work is showing how stable differences in agency scale into epidemic dynamics. And when these orientations are embedded in an epidemic model, they give rise to different epidemic trajectories. Vaccination behavior, therefore, emerges from a landscape of psychosocial diversity. And when that diversity is taken seriously, policy can become both more effective and more socially legitimate. Thank you.
Thank you very much. I think it's question time. So, yeah. Question. Claudio, start. Question. No. People online to them. Online, do you have questions from any of the online participants? You can indicate if you have questions. Okay. Right, so maybe I will start from here. Then if you have some online participants who want to ask questions, you can come after. Thank you very much.
All right, thank you so much, Andre, for that beautiful presentation. In the model finding, we saw that going for targeted vaccine age group actually leads to less number of cases, and then for target behaviors, we are having averting more deaths. Now, okay, but in the model structure, I'm interested in how the vaccine was actually incorporated into the model in such a way that the age groups and the behavioral aspect of it is which was captured. I want to know, could there be also that maybe because when you talked about if we go general, give the intervention generally vaccine, and it seems not to be performing compared to the other ones. I don't know, could there also be some factors that may be responsible for that? Will it be that because now we want to spend less money, not to do mass vaccination if targeted can do, but then let's be sure that there are no biases, in our model structures and all of that. I just want to be sure that how we finally arrive at the point where we had to get very, very insightful results. Yeah, thank you.
So let me summarize the way that vaccination enters the model and let me know if this addresses your question. So we have done two different kinds of models, only one of which I presented here. In one, we assumed that there were no age differences, which we know, of course, is not true for respiratory infections where close contacts are highly age structured and assortative. And then in this case, we assumed that there were age differences and that most of the vaccination attitudes could be summarized according to age cohort. And so by looking at the general uptake among different age cohorts in the US, as well as the psychologically measured intentions to vaccinate, we found that by vaccinating older individuals, we actually did not reduce cases as much as if we had vaccinated younger individuals, but we prevented severe outcomes, severe disease and death, hospitalizations and death at a greater level. Ideally, what one would like to do is actually intersect both the health decision-making preferences, the psychological attitudes, and the age cohorts. Our current model is something like, I guess, 60 dimensional, so 60 different state variables. And if we were to cross that with decision-making preferences, we would have something that would be many hundreds of differential equations. Well, we thought it would be that was too complicated, which is why we're moving up in sort of, we first developed a model that just stratified by health decision-making preference. Now, today, I've presented a model that just stratifies by age, but it's sensitive to what those preferences are. And then we would like to, in the future, develop another model, perhaps an agent-based simulation that brings both categories together completely. Does that answer your question?
Yeah, very well. The insights already. Thank you. Okay, next person.
Okay, yeah, I think that he's saying that the question is in line, but then I also was going to say that the data structure was the model fitted to? What kind of data was the model fitted to?
So
Yeah.
it's actually one of the things that I think is most remarkable about this model is we did very little fitting or calibration. So almost all of our parameters are measured directly. Things like age-specific vaccination rate. There was one constant which moderated the transmission rate. So it was basically a constant in front of the contact matrix, which we hand-tuned to roughly fit a typical outbreak season. I think because we didn't actually fit the model, it's remarkable that it fits the typical US influenza season so well.
Any other question from the online participant? Question of the online participant? Anyone? Okay. Okay, so maybe I should just make one or two inputs. Like I realized that during the last COVID in Nigeria, we observed that people were developing some models averagely for the population. They are considered the average when you have the normal SIR and all that. And you find out that it was quite difficult to really understand how the disease is spreading and how to specifically measure the prevalence at each age groups, because when you already generalize, it could be very misleading. So at the end of the day, we found out that the age structure model was going to be very, especially because of the population pyramid of Nigeria. Different countries have different population pyramids. And then, so you have to look at this. And then when that was put in place, we saw that the younger population in Nigeria were actually more than the older population. So which did not allow COVID to really spread the way it spread in other countries, because the younger population had COVID, and after some time they survived. They could beat the situation. So I think from my own point of view, I would have loved to really, because this kind of model, it's not does not really require a kind of computational intelligence, but it's what I see there is that it's going to be like massive, like what you have just said now. You have to repeat. If I build SEIR, so I'm going to, depending on the number of age groups I have, if I have different, like 4 or 5 age groups, so it's going to be like maybe 5 times 4 or 5 times 10, depending on the number of classes of age groups. So I'll be interested to have seen the way the different parameters of the model were put together, to be able to really understand the flow, in case some people are interested in going through this kind of modeling going forward. Thank you very much.
So I think the question has to do, and tell me if this is correct, with the fact that different countries have different demography, so different age structure.
Yeah.
And this means that the outbreak dynamics of a given respiratory infection, say SARS-CoV-2 or influenza, will differ from country to country. Yes, so I completely agree with that. And it's actually one of the points that this work underscores. One paper that I would recommend to you is due to some of my colleagues, Pej Rahani, Zhu Zhang, and Aaron King. It's from Science in 2010. Contact network structure.
Is it possible to type on the?
I'll put it in the chat. Okay. Contact network structure explains the changing epidemiology of pertussis. It's a paper that I have all of my students in theoretical epidemiology read, because it's, I think, really central to underscoring this issue that variation from country to country in demography really affects disease outbreaks. Now, I think it affects them in two specific ways. One has to do with contact patterns, and the other has to do with vulnerability to severe disease. And so I think we see this both with influenza and SARS-CoV-2. I think it would be really fascinating to do research that allowed one to compare, say, Nigeria and the United States, in order to see how that different age structure actually affects these respiratory infections. I'd also be quite interested to understand better how the health decision-making preferences, what I talked about at the beginning of this talk, differ from society to society, as we've only measured it for the US. So I'll go ahead and put that paper in the chat now.
No, it's not done. It's trying to put on someone. He's trying to write you a paper here.
I see a hand raised online. If you're able, perhaps you can ask your question or put it in the chat.
Yes, thank you so much, Professor Drake, for the beautiful webinar. Although I'm not into mathematical modeling, but I'm into molecular epidemiology. I quite agree with the points that you have raised on the patterns that is being observed with regards to people's behavior about vaccination. However, as you have concluded, community or demographics, is will come to play in some, particularly in sub-Saharan Africa. I was conducting a survey on vaccine hesitancy among caregivers, basically on malaria. But, I tried to ask if they had at one time or the other, displayed hesitancy to any vaccines. And most of those that responded to that section said yes to COVID vaccine. And I also asked why was that? I think basically it's the misinformation that turned to be, the highest response, by the responders. So misinformation sometimes, is crucial because some of them what it has no scientific basis is what will be carried, to give people, about, such vaccines. Then I also want to ask that, well, I don't know if it's applicable. Most of the disease patterns that you have mentioned has to do with diseases that cut across age groups. But what of in the case where the caregivers are the ones that makes the decision? Like in the case of malaria, for example, the child, has no say because in terms of consent, it's the parent or guardian of that child that will have to make the decision. So what comes to play? Thank you, sir.
Yeah, so those are great questions. So first, to address the issue of misinformation. As I mentioned during my talk, I actually think misinformation and information is very important. And many social scientists have measured that in survey studies. Our point here is that even after you've corrected issues of misinformation, there are still stable psychological dispositions that differentiate whether people will receive a vaccine or not. And we provide a structured, a new theory, basically, to explain why that is. In terms of the issue of caregivers making decisions for their children, in fact, our survey and our analysis is based on the assumption that children will receive the same treatment that their caregivers prefer for themselves. We did not survey children for their individual beliefs, but their parents.
Yeah, that's right. They are at the mercy of their parents. You're right.
You have answered my second question. Like the parameters in the model, because you're having a large system and then there'll be a lot of parameters and all that. And, so how did you being able to look at the effect of each of the parameters on the model, given that you have a large systems of equation?
So I think the question asks, how did we do sensitivity analysis to the parameters given the large system of equations? The truth is we haven't done that yet. This is just a first order analysis that I'm presenting here for the first time. And that is something that would need to be done. We would probably do it through a perturbation type analysis. My usual approach is to sample within a range around each of our notional parameters according to a Latin hypercube. And then summarize the outcomes of running a large set of randomly sampled parameters through the model.
So did you compare two different locations for this particular data you are looking at? Is the data coming from different geographical location?
So the data that we used are just the psychological data or the crude summary of what an annual flu epidemic looks like in the US, which is just a range of outcomes. To calibrate the parameters, we mostly read these off of the population level statistics. So for instance, from our survey, we know what the vaccination rate for each age is. From the polymod study, we have the age assortative contact rates. From national statistics, we know what the disease-induced mortality rate is for vaccinated and unvaccinated individuals. We have the birth rates based off of the population statistics. The only thing that we calibrated was a prefactor in front of the contact matrix to regulate the transmissibility. And we did that informally by just picking a value in which our statistics roughly matched a typical influenza season in the US. Typical influenza season in the US may differ by several weeks in terms of when its peak is, as well as a factor of 2 or so in terms of total cases.
Now, you are looking at epidemic. Now, looking at the aspect of uncertainty, like you have used a deterministic model. So how do you think this will be able to like capture what is going on? Because I know that when there is epidemic, or especially when especially when there's an epidemic, the best option is to use the stochastic model to be able to capture, the behavior of that disease, especially in a very, very small time interval. Over.
Yeah, so I think you're right. And for instance, when we develop models for forecasting, when we develop models for inference on parameters, we almost always use stochastic models with a stochastic observation process. I mentioned in the slide where I was setting up the model that that was not the intent. In this case, it was primarily explanatory to understand what the impact of different strategies for vaccination targeting these different groups, what the probable effect would be. And so in that sense, it really is just a mean field model with an average effect.
Okay, thank you very much. I don't know if there is any other question. Well, the absence of other question, can we give John Drake another thought? Okay, we are done for giving us the opportunity to give a talk. This is the first talk in 2006. We appreciate you. Thank you.
And thank you for the invitation to speak.
So have a nice day. Bye.